Hi, I'm Prof L and welcome to Chemistry Matters. And today we are going to do a calculation with a weak acid. Okay, so in previous videos we have done calculations using strong acids. Today we're going to do the calculation using weak acid, and we're going to find that it's very, very similar to some calculations that we did in previous videos when we were looking at equilibria, and in particular using a concentration table. So let's get into it. Okay, our question we're going to answer today is, what is the pH of a solution, 0.500 mole per litre solution of acetic acid, CH₃COOH, properly called ethanoic acid, if we want the proper IUPAC name. Okay, so we want to find what the pH of that is, and the one piece of information that we're going to be given in order to help us with this is that the Ka of acetic acid is equal to 1.8 times 10 to the power of -5. How do we do this? Right, so first of all, we know it's an equilibrium process. So if it's an equilibrium process, let's write the balanced equilibrium equation for what's going on here, okay? So H2O plus CH₃COOH is in equilibrium with CH₃COO minus plus H3O plus, everything of course being aqueous except for good old water. Okay, so it's an equilibrium process. We've got a 0.5 mole per litre solution of this. We're not given a heck of a lot to go on here, but as we've seen in the videos on doing calculations involving equilibria, perhaps we could use a concentration table here and it might make things a little easier. So let's do that. Let's set up our concentration table, initial, change, and equilibrium concentrations, okay? So we'll set up the whole thing just as we've done before. Put it into grids and realize that, okay, we have got 1, 2, 3, 4, 5, 6, 7, 8, 9 grids or blocks to fill in our grid, okay? So, what do we know? What is the piece, or what are the pieces of information that we've been given in the question? We're told we have a 0.5 mole per litre solution of acetic acid. So the initial concentration of acetic acid is going to be 0.500 mole per litre. We know that, okay? We're told nothing else essentially to help fill us, or help us fill this out. So that's the data that we've been given, the datum indeed that we've been given. The initial concentration of acetate before any reaction has occurred must be 0, and we're going to assume that the initial concentration of H3O plus before any reaction has occurred is also 0. Okay. So we're not given any equilibrium concentrations or anything like that, so we are going to have to resort to unknowns. Okay. So we're going to say, right, we've got 0.5 mole per litre acetic acid. We know that's going to dissociate a little bit. Okay, it's a weak acid. It's going to dissociate a little bit. It's going to go to the right a little bit. So therefore, the concentration of this is going to change a little bit, and it's going to change by what we're going to call -x. And the concentration of this from the stoichiometry, if this goes down by an amount -x, this must increase by an amount +x. And again, from the stoichiometry, 1 to 1, this must also increase by +x. And so therefore, that gives us now our equilibrium concentrations. This is going to be 0.5 minus x. This is going to be x, and this is going to be x. Okay. And you might think, okay, well, that's great, but where does that leave us? Okay, well, we know the equilibrium concentrations of now this and this and this. So a good idea might now be to write the Ka expression and see what we can do with that. So in this case, Ka is going to be equal to the CH₃COOH minus times H3O plus concentration over the concentration of CH₃COOH, the acetic acid, undissociated acetic acid concentration. Okay? So, let's get a little bit more room here. And we have shown from our concentration table that these are the values. So, the acetate concentration is X, the H3O plus concentration is X, and the CH₃COOH concentration is 0.500 minus X. And we know, because we were told, that the Ka value is equal to 1.8 times 10 to the negative 5 for this. So, in other words, here's the equation that we need to solve. So let's get rid of this now. That's served its purpose. And let's then, squeaky table, let's then solve this. Okay. So as we saw with our calculations on just equilibrium systems, this looks very much like a quadratic equation, and in fact it is. Okay. So we can say, therefore, x squared, x times x is x squared, is equal to 0.500 minus x multiplied by 1.8 times 10 to the minus 5. Then we can multiply that out as x squared plus 1.8 times 10 to the minus 5x minus 9.0 times 10 to the minus 6 is equal to 0. Okay? We get this quadratic by multiplying this out. Okay, we're going to have 0.5 multiplied by 1.8 by 10 to the minus 5, that's 9 by 10 to the minus 6. And then we're going to have a 1.8 by 10 to the minus 5x term here. Okay, so then you put that into your solver of choice, you use your calculator, you go online or whatever, and then you find x, obviously we have two roots here. X can be minus 0.003, and we know that that's not going to be happening because that'll give us a negative concentration. Or, funnily enough, x can also be exactly plus 0.03. That's the one that we're going to be using. Okay? So in other words, if we go back to our concentration table, we said that x was the concentration of H3O plus at equilibrium. Okay? So the H3O plus concentration from the concentration table is equal to x is equal to 0.0030. Okay? So then for the pH, we take the negative log of that, and the pH of that then comes out at 2.52. pH of 2.52. Okay? And that's your weak acid, okay? If this was a strong acid, it would have a pH below 1. It's a weak acid, it's got a pH of 2.52. Okay, if the H3O plus concentration is equal to X is equal to that, then also the acetate ion concentration is equal to X is equal to 0.0030, and we should put mole per litre there, shouldn't we? Okay, mole per litre, just to be absolutely clear about that. And the interesting bit, well, heck, it's all interesting, but let's have a look at what the concentration of CH₃COOH is, because it started off at 0.500 mole per litre. From the concentration table, we said that it is 0.500 minus X, and X, remember, is 0.003, and so that equals 0.497 mole per litre. And that shows you that acetic acid really is a weak acid. You start off with a concentration of 0.5 mole per litre, you put it into water, you end up with a concentration of 0.497 mole per litre. Okay? It's hardly dissociated at all. So very much a weak acid. Okay, so in order to solve this equation, what we have done is we've solved it exactly. We've used the quadratic formula and we've solved it exactly. Do we have to use the quadratic formula? The answer is no, we don't. And that comes as a consequence of the fact that we're talking about weak acids, okay? We said that the Ka is equal to x squared divided by 0.500 minus x, okay? And we said that that was equal to 1.8 times 10 to the power of minus 5. And then we rearranged that, it became a quadratic, and we solved the quadratic exactly. Now, we can make an approximation and solve it quickly. And the approximation that we are going to make is that 0.500 minus x is approximately equal to 0.500. In other words, we're assuming that the weak acid doesn't actually dissociate at all, which sounds a little bit weird, but it actually works, okay? So if we assume that 0.5 minus x is basically equal to 0.5, we can then rewrite this and say that Ka is equal to x squared upon 0.500 equals 1.8 times 10 to the minus 5. And all of a sudden things just got way easier, okay? Because therefore x squared is equal to 0.500 times 1.8 times 10 to the minus 5, which is equal to 9.0 times 10 to the minus 6. Okay? Therefore, x is equal to the square root of 9.0 times 10 to the minus 6, which is equal to, surprise, surprise, 0.003 mole per litre. You get exactly the same answer as you do when you use the quadratic formula, okay? The reason that this works is precisely because acetic acid is such an incredibly weak acid. And it dissociates very, very little, as we saw in the exact solution. You start at 0.5, you end up at 0.497. So really, this is a good approximation, okay? And a lot of the time, you will find that you can make that approximation. The only time that you're not really able to make that approximation is when you are talking about very dilute solutions of very weak acids. And hopefully your instructors would not be nasty enough to give you a question like that. Okay, so that's basically the way, or two ways, that you can do these types of problems. You can do them exact and solve a quadratic, or you can make the assumption like this, or you could use an equation. And the equation that you can use, which actually comes out of the assumption, is that the H3O plus concentration for a weak acid is equal to the square root of the initial concentration of the acid multiplied by the Ka of the weak acid, okay? And this equation here is, in fact, exactly what we have down here. It's exactly the same thing, okay? So you could remember that equation, you could do the quadratic, or you could make the approximation, okay? Now there's one thing that we've overlooked in all of this, and in fact in all of the acid-base problems that we've done thus far. And that one thing that we have overlooked is good old water. Because remember, we can get water plus water giving H3O plus plus OH minus. In other words, water can contribute to the total H3O plus in our solution. So the question then becomes, right, is this going to be a problem? Does it make a difference to our answer? And in this case, the answer is no, it doesn't, because the maximum possible H3O plus concentration that you can get from pure water is 1.0 times 10 to the minus 7 mole per litre. That's the H3O plus concentration in pure water. In practice, we find that this number is going to be even less because of the fact we have other acids in our solution. And so therefore, we can safely neglect any contribution of water to the total H3O plus concentration of our solution, provided that we're not talking about, again, very, very dilute solutions of very, very weak acids. Okay, so there you go, a couple of different ways of doing weak acid calculations. Now, of course, we don't have time to do weak bases, but a weak base type calculation is entirely analogous. The only difference is that you're going to be using Kb rather than Ka, but everything else is exactly the same. You set up the concentration table, you can make assumptions, you can solve a quadratic, do whatever, and it's entirely the same process. Okay. Right, and having said that, I think it is probably time to knock it on the head. So we will see you in the next video.